Okay, welcome to part two of bond breaking and bond forming. Um, okay, so in the last video, I presented how you go about analyzing a chemical reaction to determine what types of bonds are breaking and what types of bonds are forming. So now I'd like to say in words another chemical reaction and see if you can write the balanced chemical reaction, and then we'll go forward from there and tackle numbers 2, 3, and 4 from our checklist. Okay? All right. So I'm going to read, I'm going to say in words a chemical reaction, and I'd like you to then pause the video, write the chemical equation, and balance it. Okay, so this is good practice. Here we go. Propane burns in oxygen in a combustion reaction. Propane reacts with oxygen in a combustion reaction. So that should tell you everything you need to know, certainly about the products, since you know it's a combustion reaction. Propane, what's propane? Well, I would go back, check your notes in the unit on organic chemistry, and I think you'll find there both the chemical formula as well as the structural formula for propane. So go ahead, check your notes, and push the pause button, and then see if you can put that together. Okay, hopefully you're back and you've got everything in place. But let's go over this. Let's see how you did. All right, propane. That's the 3-carbon chain, the simple hydrocarbon. So the chemical formula is C3H8, and I mentioned that it's burning in oxygen. Classic combustion reaction, and the usual products are carbon dioxide and water. Okay. Now to balance this thing, you can immediately see that you've got the carbons are out of whack, the hydrogens are clearly not balanced. Let's take care of the carbon first. All right, we've got to put a 3 there. We have 8 hydrogens on the left, 2 here, so a coefficient of 4 takes care of that. And now let's take a look at the oxygens, because clearly they're not balanced. All right, how many oxygens are coming from carbon dioxide? 3 times 2 is 6. How many oxygens from water? 4. 4 times 1 is 4. And so the total number of oxygens on the product side is 10. Okay, so that means we got to put a 5 here, and now everything is good. All is well in propane land. Now let's, I'm feeling like blue here. All right, now hopefully you found the structural formula for propane. Let's just double check here. We've converted the word equation and we've balanced it. We got to restate the reaction in terms of reactant and product molecules. Okay, then we'll do the structural formula. Okay, so in words we would say 1 molecule of propane, you get a little thinner, reacts with 5 molecules, okay, 5 molecules of oxygen to form 3, so that's what the balanced chemical equation is telling us, right? We're going to form 3 molecules of carbon dioxide. And as I'm writing this, just know that this is exactly what I expect you to write when I ask you to, express the reaction in terms of the numbers of reactant and product molecules. 3 molecules of carbon dioxide or plus 4 molecules of water. Okay. But I know you'll write much neater than I am. I apologize for my messy script. But you get the idea. That's what the balanced equation is telling us. Okay, now number 3. We need to draw the structural formulas for each of these compounds and draw the correct number as indicated by the coefficients. So hopefully you found the structural formula for propane in your notes. It's a 3-carbon chain connected by single bonds, and then the other valence positions are occupied by hydrogen atoms. Okay, so that is a propane molecule depicted in structural formula form, and it's reacting with 5 molecules of oxygen. So literally, I'm going to draw 5 molecules of oxygen, and just bear with me. I'm going to use like a line to indicate the non-bonding electron pairs, because my stylus is not very good at drawing individual dots. Okay, so I just want you to know, we understand that each oxygen has 2 pairs of non-bonding electrons. Okay, so when 1 molecule of propane reacts with 5 molecules of oxygen, what are we going to get out of this deal? Well, looks like we're going to get 3 molecules of carbon dioxide. Okay, plus 4 molecules of water. Okay, I'm drawing this kind of quickly. Okay, and we realize that there are 2 non-bonding electron pairs on each oxygen. Okay, so there you have it. This is what's really going on. If you want to burn 1 molecule of propane in oxygen, well, buddy, it's going to take you 5 molecules of oxygen to do that. But what you'll get out of the deal is 3 molecules of carbon dioxide, 4 molecules of water. And I would be negligent if I didn't also tell you that you're going to get an awful lot of heat out of this reaction. So, and that's typically what you're really trying to get out of the reaction, is the heat energy, right? So that you can cook your food, warm your house, or whatever. Okay, now let's go back and see where we are. Okay, so we've drawn the structural formulas. Now we need to identify the unique chemical bond types. All right, so we're kind of like little chemical taxonomists. We're going to go and try to identify these different types of bonds. Okay, let's look at propane. All right, so I immediately see a carbon-carbon single bond. Okay, we have one here and we have one there. Okay, so carbon-carbon single bond, and there are 2 of them. And then I see a lot of carbon-hydrogen single bonds. So let's draw that. And how many of those are there? Well, there are as many carbon-hydrogen single bonds as there are hydrogens, which are 8. So we've got 8 of those. Excuse me. And then we have 5 oxygen-oxygen double bonds, correct? So oxygen-oxygen double bonds, 5 of those. Okay, so that's what we have on the reactant side. Now let's go over and see what's going on the product side. Okay, it looks to me like we have a number of carbon-oxygen double bonds. Okay, so there's a carbon-oxygen double bond here and here, there and there. That's 3 and 4, 5, 6. Okay, so carbon-oxygen double bond. Sorry, we have 6 of those. And then over here, among the water molecules, we have hydrogen-oxygen bonds, single bonds. Okay, and there's, I think you can see pretty fast that we have eight of those. So that's hydrogen, oxygen, 8 of those. Okay, so to sort of summarize, when you react one molecule of propane, what's going to happen in a combustion reaction is you're going to break 2 carbon-carbon single bonds. You're going to have to break 8 carbon-hydrogen single bonds and 5 oxygen-oxygen double bonds. Okay, so that's the carnage that's going to occur during this reaction. And also, just to kind of foreshadow a little bit when we get to thermochemistry, breaking a chemical bond, that's not free. That takes some effort, and more precisely, it takes energy to break these bonds. So you're putting a lot of energy into the process. It costs a lot of energy, but on the flip side, when you then form 6 carbon-oxygen double bonds and 8 hydrogen-oxygen single bonds, that releases a tremendous amount of energy. You get a return on your initial energy investment, and you get so much back, in fact, that the net energy it makes for a very exothermic reaction, and you get a lot of energy out of it. Okay, so as long as you understand, clearly you're doing well with converting the word to the chemical, equation formula. You're doing pretty good with balancing, I hope. I hope this reaction was, fairly straightforward to create and balance. And then this piece here, describing the reaction in terms of the numbers of reactant and product molecules involved, that should be pretty straightforward. And then this piece, as long as you know the structural formulas, you can generate them on command. Then I think, hopefully it's looking like pretty straightforward, itemizing each of their unique bond types and tallying things up. So this is what we need to be able to do, and that's the end of this presentation. Okay, thanks.